Alright guys, welcome to the second kind of technical lecture of the course. This is our first one kind of focused on hardware and how a computer works and what the different pieces are. And this one's going to focus on kind of networking and how computers communicate and transfer data from one computer to the other. So here's our funny internet picture of the section. And essentially this is a VPN for purposes of this class is essentially similar to what a proxy is, right? So it's funny because the drink is going from here through this proxy to the ultimate end user here, which is allowing a middleman or a computer between you and who you're communicating with that is handling the communication back and forth. So first we got to talk about the difference between the internet and an intranet. So essentially, the internet is the worldwide collection of computers that are all communicating back and forth. It includes everything from, the World Wide Web to your bank to your favorite video game. All that stuff operates on the internet. Okay, an intranet is any smaller, usually geographically localized small network of computers. So for instance, in my house right now, I have an intranet that consists of the desktop that I'm recording this on, plus my wife's laptop, my cell phone, my wife's cell phone. So those computers are all on their own small network just here in my home. And then through a router, all four of those computers connect to the outside world. But even if the internet went down, my internet service provider, there's a storm and the internet goes down, my computers can still talk to each other, this computer with the laptop, with my cell phone, even without the internet, because they have their own smaller network called an intranet. Okay? When my computer, like the one I'm recording this on, is getting information from another computer, that's a download. When it's sending information to another computer, that is an upload. Okay? So if I'm watching Netflix is very, very heavy on the download because I have to get all that video from Netflix's servers across the internet to my house. That's a lot of data that Netflix has to send to me. That's a heavy download, but the upload there is minimal, right? The only time I would need to upload anything is if I, say, request a new episode of whatever I'm watching at the time, or I want to update my Netflix account. And those are all very small, very easily done things. So the upload speed isn't nearly as important as the download speed for purposes of watching Netflix. Now, if I'm playing a video game, PlayerUnknown's Battlegrounds or 7 Days to Die or any of the big video games that I'm currently playing these days, download and upload become a little bit more important. Upload becomes a little bit more important compared to the download because I need to send a whole bunch of information to the game. Every time I click a button to pick something up or to shoot a weapon or to do a thing, that has to be sent from me to the server it's communicating with. So upload becomes a little bit more important. On YouTube, if I want to post a video to YouTube, as I will do with this video once I'm done recording it, then upload is very important and download not so much, right? Because I am sending information from my computer to YouTube, and thus the upload is the important one. Now, most of the time, the internet service providers in your area almost guaranteed will give you a much better download speed than upload speed. That's because for most things most people do on the internet, download is more important than upload. So for instance, right now on this computer, here, in fact, let's test it. Let's go and test and see. You can test your download and upload speed just by doing a Google search for speed test. Here's an Xfinity one. Xfinity happens to be my personal internet service provider, so we'll go ahead and check this one. So if we just click Start Test, it'll show us our download speed. Pretty good, 120-ish megabits per second. That's a very good download speed, but in a minute we're going to get an upload speed, and I'm betting it's going to be far less than 125 megabit. Yeah, see, mid-20s for upload. So that's not nearly as fast as our download speed, and that's normal. That's how internet service providers will usually run their services. So Comcast or Xfinity is my internet service provider. They are in charge of the link between my house and the larger global internet. You know, at your house, you might use AT&T, you might use Time Warner, you might use Cox. There are a bunch of internet service providers, and they're fairly geographically distinct. So in any one city, there is usually one good broadband service provider. Now, there's always things like satellite internet or DSL internet, but those are usually not as good as cable or fiber. But those are each run by disparate companies. The internet backbone, those are the really big connections between major centers, you know, the connection between New York and Washington, D.C., and the connection between Washington, D.C. and Chicago, and those kind of things. Those kind of very important, big, heavy-duty connections between disparate geographic areas. In the United States, basically there are 5 or 6 companies that control the vast majority of that. It's, you know, there's Qwest, Verizon, Sprint, I can't remember all of them, it doesn't matter, but there's a very small handful of companies in the single digits that control a huge majority of the internet backbone infrastructure in the United States. So the kind of analogy here is with roads. You're going to hear me use this analogy a lot. Computer scientists don't really like it sometimes, but you know what? We're not a computer science course. I really don't care. So in essence, the ISPs are the residential roads. They're the small connections that you drive on to get from your driveway to the interstate. The backbones are the interstates. They're the big, giant connections that have lots and lots of traffic, lots and lots of data going over them. So essentially, you are paying your internet service provider only to connect you with this larger backbone. Okay? So how does it actually work, though? How does internet communication work? Well, there has to be rules, right? For any computer to talk to another computer, there has to be a set of rules, and we call those rules a protocol. The biggest protocol on the internet is what's called TCP/IP. Okay, TCP/IP is a set of rules governing how any two computers are going to communicate over the internet. There are others like UDP and a few others, but those are less important and less common on the internet for normal end users like you and me. But one thing that TCP/IP does is it connects you with another computer, and it does a handshake, right? So essentially, when you first try to connect to a website, your computer will send a message to the website server saying, hey, I would like to communicate with you. Is that okay? Then the website says, sure, that's okay with me. I'm going to communicate back to you. Is that okay? And your computer says, yes, that's fine. And then a connection is established. That's called, it's like a handshake, okay? Where two computers agree to send information back and forth. That's part of the rules, the protocol that TCP/IP has whenever it communicates from one computer to another. Now, one of the reasons, probably the biggest reason why the internet is such an interesting, versatile amazingly productive communication network is because it's what's called a packet switched network. With the networks that existed prior to the internet, essentially things like the telephone system. The telephone system was a network. I could pick up my phone and I could call somebody in New York or LA or China or Paris, and I would talk to them and then hang up the phone. But that wasn't a packet switch network. Essentially, when I called somebody in Paris, there had to be a physical line connecting me to the person in Paris. And as long as me and the person in Paris were talking on the phone, that line was taken up by our conversation. Nobody else could use that one particular line. Okay? With a packet switch network, as many people as possible can all share one line at the exact same time. Because each message that you send is cut up into teeny tiny little chunks called packets, usually just a few bytes or a few kilobytes in size. And then that packet is sent from you to the receiver through a bunch of different nodes, right? So if I want to talk to on the internet to somebody in Paris, it doesn't tie up the line. I just split my communications into tons and tons and tons of these teeny tiny little packets, and those packets go from me to my internet service provider's computers, and they bounce, might be routed through a few of their computers, then onto the internet backbone, and then, routed through a few of those computers, and then to the person I'm communicating with, ISP, and through a few of their servers, and then finally to the person I'm communicating with. But each packet doesn't tie up the line. So imagine each packet as a marble, and each data connection between me and my ISP servers, the ISP servers to each other, or the backbone servers to each other. Imagine those pathways as like a tube, like a hose, right? So just because my packets, my marbles, are rolling down that tube from one node to another node, doesn't mean that other people can't shove their marbles in at the same time, right? Those packets get to the other end of that tube, that hose, and the computer on the other end says, okay, this marble, this packet, I need to send down this other tube to this next node on the chain. This packet I need to send down this node. This packet I need to send down this node. That process is called routing. So there's some computer or some mechanical or computerized device at the end of each hose that takes each marble or each packet and sends it on its way to the next node on the chain, right? Now, what's interesting is, with this packet switch network, not all of my packets are going to take the same route between me and the person I'm communicating with, right? So here's a good illustration of how that works. So here's me, here's the person I'm communicating with. Now, my first packet comes out and it's on the green line. So it gets to my ISP servers and it says, what's the fastest way between here and here? Well, it involves sending the packet to here. What's the fastest way between here and here? Well, it involves sending the packet here. And these messages, these packets, the first packet goes along this green route between me and the person I'm communicating with. But then the second packet comes in, and this, the green line, is no longer the fastest route to get from point A to point B. So it sends it on a different route. It goes this way to point B, right? And then my third packet goes along the red line. And it's got a completely different way of getting from me to the person I'm communicating with. But then the person I'm communicating with, their computer gets all these packets together. Once all the packets are in, it says, oh, that's the entire message, and it takes each of those little individual packets and makes them into one giant message again. It could be a file I'm sending. It could be a video that I'm watching. It could be any kind of data that I'm sending from one person to another. It all gets split up into those teeny tiny little packets. It all gets routed from me through this giant collection of other servers to this person I'm communicating with. Now, how does this node know who I'm sending it to? How does this node know what the ultimate destination of that packet is? Well, two things. One, each packet has a header. It's just kind of, if you use the analogy of like an old snail mail envelope, the header contains the where are you going to, the address, where is this letter supposed to be delivered, right? So the header says, hey, I am a packet, I am TCP/IP protocol, I am headed to this address. Can you please forward me on to the next stage in that delivery? These addresses, though, are not like physical addresses. They're not like a street address like you would use on an envelope. They're what's called an IP address, or an Internet Protocol address. These Internet Protocol addresses, using the old system that we're trying to switch away from as I'm recording this, are 4 numbers separated by a period. So it's 1.2.3.4, or 187.50.12.1, right? That is an IP address. Each one of those 4 numbers can range from 0 to 255. Now you might be asking yourself, 255, that's kind of a weird, odd number to stop at. Why 0 to 255? Why not 0 to 1,000? Why not 0 to 999? Well, because you as a human being are thinking in decimal. The math that we do around the world is all based on base 10, i.e., you go up in the single digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but that's all you can do with a single digit. Now you carry over that single digit to the next place, the tens place. So you have a 1 in the tens place, and then a 0 in the ones place, and that means 10. Computers don't think like that. Computers think in base 2, zeros and ones. So they go from 0 to 1 to, now there is no 2, so they have to go put a 1 in the next place, which is the 2's place, and then back to the 1's place, right? So instead of the 1's place, the 10's place, the hundreds, 1,000s, it's the 1's place, 2's, 4's, 8's, 16's. That's how a computer thinks. So a nice round number in decimal, like 1,000 or 10,000 or 1,000,000, that's a nice, a 1 followed by a bunch of zeros. That's not how computers think. For computers, the nice round numbers are 2, 4, 8, 16, 32, 64, 128, and 256. So 0 to 255 is 256 different options. So that is a nice, perfectly round number in binary. Even though it seems like a kind of a weird number for us because we think in decimal, 256 is a perfectly nice round number in binary, which is the way computers think. So those IP addresses are 4 numbers separated by dots or periods, and they can range from 0 to 255, okay? Each one. So if you do the math, that's 256 times 256 times 256 times 256 different combinations of IP addresses. Now, when the internet was first made, when TCP/IP first came out, when these IP addresses first started being assigned, that huge number, a couple of billion, was like, oh, that's more addresses than we'll ever need. The problem is, now in the 21st century, that's not enough. We need way more IP. There are more devices connected to the internet than have these individual IP addresses. So we're switching over to a new system, which will have way more possible combinations of numbers, so these IP addresses can be unique again. Does that make sense? But the problem is, humans are really bad at remembering numbers. Computers are great at remembering numbers. Humans, not so good. So every time I want to do a Google search, I don't have to remember 57.82.15.12, which I'm just pulling random numbers, but that might be the IP address of the Google server. I don't have to remember that because there's a process connected to the internet that does that for you. So all I have to remember is www.google.com. I can remember that. That's easy, right? Because humans love thinking in words, and things like google.com or yahoo.com. Right? Those are easy for us to remember. But computers, those words don't make any sense. Computers don't know what words mean. Computers want numbers. So there's this process that they go through called DNS, the Domain Name Service. Essentially, when I tell my computer, go to www.google.com, my computer says, okay, but I don't know what google.com means. So it contacts a DNS server and says, hey, DNS, can you translate www.google.com into an IP address that I can understand? And the DNS server says, sure. The IP address for google.com is these numbers. Now my computer says, oh, thank you very much. Now I know who to talk to. Now it sends off the packet to google.com, but using the IP address instead of just the words or the letters that make up google.com. So the DNS service is the way to translate from kind of English to binary or IP. Okay? So we've got a packet. Starts here at my computer. I want to send it to this server in Google. The first thing my computer does is it says, hey, what is the IP address for google.com? DNS comes back and says, oh, the IP address for google.com is number.number.number.number. My computer says, thank you very much, takes my message and divides it into little packets. Each packet in the header says, can you please forward me to such and such IP address, which is Google's IP address, and sends it off. Now, each computer that it comes to figures out what the shortest path to get to that IP address is. They all eventually make their way to Google, and Google reassembles them in order, because the other thing that the header has is what order the packet is in, right? So packet number 1 is labeled packet number 1. Packet number 2 is labeled packet number 2. So because the packets are coming in through different paths, the google.com server is probably not getting them in the right order. They might get packet number 5 before they get packet number 3, just because of the amount of time it takes for one path versus another path. So the header also contains the order they're supposed to be reassembled in. Once they have all of the packets, they reassemble them in order, and boom, Google gets my message. Hey, send me a reply that says, who won the Super Bowl in 1975? So Google looks in its servers, finds the websites that answer my question, and send it back. And the process repeats itself. It says, okay, what IP address was the query from? I.e., my IP address. Let's send it back to that IP address. Here's the information we're going to send him back about all these different websites that answer who won the Super Bowl in 1975. We split that message into packets, and they send them back. And they go back through this process. And once they get back to my computer automatically reassembles them. And then once it has all of the packets, it puts them all in the order, unpacks them, and boom, I get my message. Now this happens in the blink of an eye. If your connection between you and Google is fast, this whole process can take well under a second, right? It goes at the speed of, it's super, 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 super fast. But that is the kind of the basic steps necessary to send any message between one computer and another computer. If that doesn't make sense, post a question on the YouTube comments thing. Now, how do we measure how fast this process is happening? Well, there's two different ways to do it. There are two different measures of speed between any two computers. So between my computer and the Google server, there are two different ways I can measure the speed of how fast that connection is. The first one, the one that's kind of the easiest to understand, is latency. Latency is basically just the speed at which one packet can go from me to them. Okay? It's just how fast can one packet make it. Bandwidth is the other way of measuring speed. And that is essentially how long does it take for a whole bunch of packets to get from point A to point B. Now, if we go back to our road analogy, which again, computer scientists don't really like, but whatever, the latency would be what's the speed limit, right? How, if I'm driving on I-95 from Miami to Washington, D.C., if the speed limit's 70 miles an hour, I'm going to get there in a much shorter time than if the speed limit was 50 miles an hour, right? So that's latency. How fast can one car get from Miami to Washington, D.C. all the way up I-95? Bandwidth is how many cars can take that path at the same time without slowing each other down, right? So I-95, fairly major roadway. It's got at least 3 lanes through most of it, so that's got fairly wide bandwidth, right? There's a lot of cars that can go down a 3-lane highway all at the same time without slowing each other down. Whereas if it was a 1-lane road, we'd have horrible traffic problems. So even though the speed limit's 75 miles an hour, nobody's actually getting 75 miles an hour because there's too much traffic. There are too many other cars trying to use that 1-lane road, right? So if we create more lanes, so more data can get through kind of at the same time, that's increasing our bandwidth. Okay? Does that analogy make sense? I hope it does. So how do we measure things like latency? Well, there are built-in commands. If you're using Windows, there are built-in commands to tell you how fast any given connection between you and whatever server you want to name is at the moment. So let's bring up a command prompt. If you don't know how to do a command prompt, you just go into the search bar, whether it's Windows 7, Windows 10, whatever. You go to your search bar and you type in CMD, right? There it is, cmd.exe, right here. We bring that up, and it will bring up a window like this, which those of old people, if you remember DOS, this will look a lot like a DOS prompt, but it's not called a DOS prompt anymore. It's called a command prompt. So we bring up a command prompt, and we just type in ping space and then an address. Now, this can be either in the English sense, www.google.com, or it can be in the IP address sense. So if we actually know the IP address of who we're trying to talk to, we can also type that in, right? But I'm going to try NFL.com. I'm a big football fan. Go Texans. So let's see what the latency is between my computer here at home and the NFL.com server, which is hosted I don't even know where. So we've sent out 4 pings now. Here is their IP address. So the NFL.com web server, their IP address is 173.222.112.56. So that individual IP address is their particular address on the internet. That is that server that is hosting NFL.com right now. Okay? Each one was a 32-byte packet, right? And this is how long it took. Okay? That's very, very quick. That's 29 milliseconds. Okay? So here's our statistics. We pinged this address, which was the NFL.com server. We sent 4 packets, and we got 4 back. In other words, none of them got dropped. None of them got lost somewhere along the way. Okay? So 0% loss. That's good. Approximate round trip time in milliseconds. The average was 29 milliseconds. So we did it 4 times just to be sure. None of our 4 packets got lost. And to get from me to the NFL to back to me took a total of 29 milliseconds. Okay? But let's say this didn't go well. Let's say 2 of our 4 packets got lost. Oh no. The question is, where is the problem? Because I'm going through probably a dozen different computers to get from me to the NFL.com server and back again. Which one of those servers is the problem? Is it my connection to my ISP? Is it an ISP problem? Is it an internet backbone problem? Or is it the NFL.com server's problem? Well, we can get some evidence about where the problem lies using the command traceroute or traceRT. So trace RT space NFL.com. Now let's see what this gives us. All right, so already we've gotten some interesting results here. So this first hop, the first thing I'm talking to, that is the IP address for my personal router. It's actually sitting right next to me on the thing here. So the packet goes from my computer to the router. That takes less than 1 millisecond, and this is the name of it. Lando Calrissian is my network name, and this is the IP address of that router. The next jump is to the first of the Comcast servers, which doesn't identify itself. It just gives its IP address, and that takes roughly 9 milliseconds. Then it jumps to another Comcast server in Savannah. Then a couple jumps later, we're in Jacksonville in Comcast, right? Then Miami, Florida, right? Still in the Comcast network. Then there's this one, request timed out. Now, because the ping on the second after this request timeout, this is still very quick, right? 29 milliseconds. That's still very quick. That tells me that this server isn't actually down. It's just set, somebody who controls that server set it to not respond to pings. So it will allow pings to go through it, obviously, because I'm able to ping things on the other side, but it won't actually respond to ping. So just because you see request timed out and star, 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 it doesn't mean that server's down. It might just mean that it's set to not reply. Okay? So here we've got this Akamai Technologies server, and that's the IP address of NFL.com, right? So NFL.com obviously hosts their website on a server provided to them by Akamai Technologies, and this is their server, right? So our packet went from my house to Savannah, Georgia, to Jacksonville, Florida, to Marietta, Georgia, to Miami, Florida, to wherever that is, to Akamai Technologies server base. And that is the path that packet took to get from me to NFL.com and then, of course, back. Okay? If I did that again, it might be a slightly different path. Because, again, every packet that's sent will choose its own path. It doesn't have to take the same path that the last packet in the sequence took. Right? But this tells me every single server that is between me and NFL.com. Okay? It's a very, very useful tool for network diagnostics and experience. Now, this image. Okay, you see this image? It's kind of hard to read. It's a very small print. But this is measures of internet speeds and costs around the world. And this is a few years old, but it's still roughly accurate. Okay? So if you'll notice, Japan has the fastest average speed, which I believe they're still the fastest today, although this number is probably much higher today. Korea's number 2, then Finland, Sweden, France. Here's the USA way down here at about 12th or 15th. Okay, the USA has very, very slow internet on average compared to most of the rest of the first world. We're not quite as bad as Australia. Australia is really bad. They're way down there. My friends in Australia are constantly complaining about the slow speed of their connections. But Japan, Korea, they have the best, fastest, most efficient internet in the world. And it's also incredibly cheap. It is way cheaper per megabyte or megabit than the United States. Okay? So, again, as this was made, which was a long time ago, a few years ago, Japan had paid 27 cents per megabit. Whereas the United States, we pay $3.33 per megabit. So they're like less than a tenth of the cost per megabit. And they also have, what? Over 10 times the speed. Right? So we here in the United States love to be, oh, America's number one. Well, when it comes to the internet, we are nowhere close. Not only are we slower than most people, we are also much more expensive on average than most of the first world. Okay? So, security. How do we protect other people from just sending messages to our computer? What's to stop a bad guy from figuring out what my IP address is and then just sending me a whole bunch of, bad packets or viruses or, whatever file they want? Well, one of the things that we have to protect us, there are many things that we use to protect ourselves on the any given network. But one of those things is what's called a firewall. Now, a firewall is essentially a guard that stands between any two nodes. You can set it up between any two nodes in any network. Usually in a home network, like in my home network, I have one firewall, and it's built into the router that I use to connect to the internet. So between the rest of the internet and all of my computers in my house, there's a firewall between them. But between, say, my computer and my wife's computer, there is no firewall because it doesn't have to go through that point. Okay? The analogy with firewalls, essentially picture a roadway. Like, the roadway is the connection between point A and point B. A firewall is an actual wall, preventing anybody from passing past it. But there are doors in that wall. In fact, there's 65,000 some odd doors in this wall. And each type of traffic has to pass through a certain type of door. So if I'm talking with a website, that's a web-based discussion, so that has to go through door number 80. Okay? If I'm sending an email, that has to go through a certain numbered door. If I'm playing PUBG and I'm talking to the server that that information is going to, that has to go through a certain numbered door. Each one of those doors is called a port, right? And if that port is open, any traffic that wants to can pass through that wall. Okay, so for instance, my firewall has web traffic open. I just want to open it up to all web traffic, so my computer can talk to any website that it wants to, and that traffic just goes right through the firewall, no problem. But if there's a certain kind of traffic that I'm not using, I should close that door. I should close that port so that no traffic can use that door to get from anywhere on the internet to my computer, right? So one of the important parts of that firewall is closing off the ports that you're not using. So there's a certain port that gets used for the PC Anywhere software. It's software that allows somebody to control your computer remotely. They can control your mouse and keyboard essentially, and do things on your computer remotely. And this is used for troubleshooting. If my computer breaks down, I can call up my IT services department, say, hey, my computer's not working. They can remote in using this software and fix my problem. So there's lots of useful ways to use this. But that can also be used by the bad guys. That would be an incredibly powerful weapon that the bad guys could use against us, right? So we don't want to just leave that open. So I'm going to figure out what port that software uses, and I'm going to close that port. So now nobody can send PC Anywhere commands to my computer and attempting to take it over, because that door is closed on my firewall. Does that make sense? Okay. Now, last thing I want to talk to you guys about is net neutrality. Net neutrality is kind of a political policy, but it's one that's very, very important to me and very, very important to a lot of people on the internet. Everything I've been talking about today is based on, there are all these servers out there, and they're all taking in packets from one place and sending them off to another. Take in this packet. Where's it headed? Okay, I'm going to send it off that way. Where's this packet headed? Okay, I'm going to send it off that way. By tradition, from 1969 until very, very recently, just in the last few years, the entire internet was neutral, meaning that every packet was treated the same no matter what kind of information it contained, no matter where it was heading to, right? The servers between me and the person I was talking to treated all those packets the exact same, whether it's Netflix data, whether it's sending an email, whether it's web traffic from me to NFL.com or web traffic from me to Facebook. All those packets are treated the exact same. Now, that doesn't mean I can't pay my ISP for more speed. That's a completely different, I can pay my ISP for more speed or more, lower latency or higher bandwidth, and that doesn't make it unneutral. But a few years ago, the internet service providers realized, hey, there's no rule, there's no requirement that we treat all these packets the same. So they started doing nefarious things like slowing down Netflix traffic. So if I wanted to watch Netflix, the quality was lower, it lagged, because my internet service provider was artificially slowing down any packets that contained information from Netflix. But then Netflix paid them a bunch of money, and all of a sudden, the speed shot up again, right? That is a violation of net neutrality. So Barack Obama, when he was president, one of the things he did, or his FCC did, was say that the internet is what's called a common carrier, like the power company or the phone company, and they can't discriminate based on the origin or contents of a packet. So in essence, like your power company, your electricity company is not legally allowed to charge you more for electricity if you plug in a GM product versus a Samsung product. They have to just charge you for the electricity, whatever that price is, no matter what brand of electronics you're using. It would be illegal for them to discriminate like that. They are forced to be neutral. Similarly, the FCC said the internet has to be neutral. These servers can't prioritize or deprioritize packets based on what they contain or where they're going to. Thus, net neutrality was protected legally, and it went back to being neutral. Just about a year ago, as I'm recording this, the Donald Trump FCC repealed that. Now net neutrality is no longer a legal requirement. And we're just starting to see different internet service providers starting to mess with the speeds that packets go through their servers. In the short term, it's going to be a minor annoyance. The big fear is that in the future, if we don't have net neutrality, internet service providers will be able to legally say things like, if you want to watch CNN, you have to pay extra. Or CNN is going to come in really slow. We're going to artificially slow it down so that you can't watch it functionally. But Fox News, that's, you can get that at full speed. So you can watch it in high quality or watch it at all. Or MSNBC, we're going to allow you to watch MSNBC because they pay us extra money. So you can watch that in high quality, no slowdown. But Fox News, we're going to cut off contact with that completely. You can't go there using our internet service provider. And CNN you can get, but it's slow, and we're going to artificially make that slower. So your internet service provider is going to be able to decide for you what websites you go to, what services you use, all those things. And that's all going to be completely legal in a non-neutral internet. So net neutrality is a very important topic for me. It's a very important topic, I think, for the entire internet, because it completely stifles any new people, right? So if a new social media platform starts under a neutral internet, it will be able to compete with Facebook and Instagram and Twitter. No problem. But under a non-neutral internet, a new social network pops up and Facebook can just pay Sprint or Comcast or Time Warner or whoever a bunch of money to say, okay, that social media website, don't allow any of your customers to access it. Or if you do allow them to access it, make it really slow and annoying to use. But give Facebook customers or Twitter customers, those people make it go fast and work great. But the new social media, don't, block it completely or slow it down or whatever. So that's kind of the big fear of a non-neutral internet. Okay? So next time you vote, make sure you're voting for people who are pro net neutrality. All right? That's the end of our second technical lecture thing. Thank you so much for watching.